Now we said earlier that the LRFD is more on a statistical approach. Now, if we draw it in terms of these curves, statistical curves, then uh, we have this plot. Okay, so this small and wider curve, this is actually the load curve, whereas this thin and taller curve is the resistance curve. Okay, so that's the resistance curve. Now, if we plot this midpoint here, it's the actually the average. So we have this mean value for the resistance side, and we have a mean value for the load side. Okay, so that's mu q sub q, and then this one is mu sub r. Okay, so you notice that the load curve is actually wider as compared to the resistance curve. So that's simply because the distance from this mid, let's say the mean or average up to this point, that's actually um, the standard deviation. Okay, so if I mean having um, a larger standard deviation just means that we have larger uncertainties, whereas in the resistance curve we have only small standard deviations. Okay, another one or another point to I mean that differentiates these two curves is that the other one is taller, whereas the load curve is smaller. So it just simply means that the resistance curve must be higher, must be greater than the load curve. So alternatively, we can just say that the factored resistances must be greater than the total factored loads. So again, it's just uh, going back to the basic idea of this designing or computation for the load combinations, that the factored resistance or the strength side, when we apply the let's say we apply the factors, must be greater than this factored loads, total factored loads. All right, so those are the two approaches. For reinforced concrete structures, we'll use LRFD. For steel structures, we'll use LRFD approach. And for timber, it's still on AST. Okay, although there are there are also available codes or specifications regarding the use of LRFD for timber structures, but for us here, I think it's still on the ASD approach. So ASD for timber, steel and RC would be LRFD. Okay, so now let's move on to the basic load combination. So we have um, the following loads. We have dead load, and letter E, that's going to be for earthquake load. Then F would be, let's say, um, flood loads, or okay, H would be lateral pressure, let's say soil lateral loads, and L for live loads. L sub R, um, that's roof live loads, and then the P and R. So this one refers to ponding loads, and R is the rain loads. Okay, so if there's a combination of these loadings that's acting on the structure, then how do we manage it? Okay, so that's what we call, or that's the term for the load combinations. Okay, so for LRFD, we have 7 combinations. So number 1 says we have 1.4 dead plus flood loads. Then number 2 we have 1.2 dead plus flood plus T. Okay, and there's a parenthesis. Okay, plus, oh sorry, I forgot. There's still self-straining force resulting or arising from contraction expansion from temperature change, that's letter T. And then wind loads, right? So wind, okay, so temperature, let's say temperature loads. Okay, so for the second load combination, we have 1.2 dead plus F plus T plus 1.6 L plus H, okay, plus 0.5 LR or R. Okay, so roof live loads or rain loads. Okay, so number 3 we have 1.2 dead plus 1.6 LR or R plus F1L or 0.8 wind. Okay, so this value F1 here is just actually notes on our lecture handouts. It says that if our floors in places of public assembly for live loads in excess of 4.8 kPa, but if it's not 4.8 kPa, then the value is 0.5. So it's either 1.0 in excess of 4.8 kPa, okay, kPa, or 0.5 if not. Okay, so that's the value. Okay, and we have also up to 7 load combinations. Okay, so it just means that if we have a, let's say, a dead load only, then you can actually cross this out. So the computation do not include this F. Okay, so if you have, let's say, dead load plus live load, then you have to just say 1.2 dead. The one that we used earlier is 1.2 dead plus 1.6 live, because we assume, or in the assumption, that we don't have this F, T, and then roof live load or rain loads. Okay, so that's why that's gonna simplify to 1.2 dead plus 1.6 live. Okay, so if there's a word or, then meaning you're gonna do a calculation or computation using LR, then another computation using R. Okay, so LR or R. Okay, so now if, let's say, we have a problem, let's say computation exercise, then what if we have this dead load, live loads, wind loads, etc., then how do we compute? Now the goal here in the computation is to find the critical loads, or the loads that would produce the highest value, let's say in terms of compression, or if it's the highest negative value for tension and stuff like that. Okay, so we'll do a sample exercise. Okay, so let's say example number 1. Now we have a dead load of, let's say, 90 kilonewton meter, and then a live load of 30 kilonewton meter. Okay, so take note that these loadings could be, let's say, the bending loads, or shear loads, or axial loads. So if it's shear or axial, then that's going to be 90 kilonewton. And if it's a bending moment, then that's going to be kilonewton and the moment arm, so kilonewton meter. Okay, so now let's consider this. We have a dead load of 90 kilonewton meter and a live load of 30 kilonewton meter. So find the critical load. Okay, so first using uh, our first combination, we have a 1.4 dead plus the flat loads. So since we don't have a flat load, then you can just say 1.4 times. So what's the dead? 90. Okay, so 1.4 times 90. Okay, so 1.4 times 90, we have 126. Okay, 126 kilonewton meter. Okay, so that's our load combination. Let's say first load combination. Then next we'll check the second load combination. So we have a 1.2 dead plus 1.6 live. So take note, I just simplified since we don't have a flood load, we don't have a roof live loads and rain loads, then we can just write it this way. Okay, so 1.2 dead plus 1.6 live. So 1.2 times what's the dead? Then that's 90 kilonewton plus 1.6 times 30. Okay, so we'll check 1.2 times 90 plus 1.6 times 30, and that's going to be 156 kilonewton meter. We can also check the third combination. So for the third combination, we have a 1.2 dead plus 1.6 roof live loads or rain loads plus F1 L or 0.8 wind. Okay, so since we don't have this LR or R, so this one is 0, the term. This term is also 0. So basically, we're left with 1.2 dead plus F1. So let's say we'll assume for now that this is 1.0. Okay, so 1.0 times L. Okay, so you'll see that this value would be actually less than, probably less than this value. We'll check. Okay, so 1.2 times 90 plus 30. So 1.2 times 90 plus 30. Okay, so that's 138. Okay, so 138 kilonewton meter. Okay, so typically, if we're just dealing with dead loads and live loads, then usually the ones that governs would be the load combination number 2. Okay, so now let's do another example for involving other types of loads. Okay, so let's say we have a dead load, live load, and wind load. Okay, and we'll try to write it in an organized manner. Okay, so dead load, let's say we have a 150 kilonewton. Okay, so for now, let's say we are solving for shear loads. Okay, so 150 kilonewton, and then for the live load we have a 60 kilonewton. And then for the wind load we have, could be let's say plus minus 50 kilonewton. Okay, so solve for the highest value. I mean the critical loading combinations. Okay, so first we'll check the loading number 1. So we have a 1.4 dead. So load combination number 1, we have a 1.4 dead plus the flood loads. So since we don't have flood loads, then that's just this simplified expression. So 1.4 dead So let's substitute the value of dead loads. We have 150. What is this value? So we have 1.4 times 150. So we have a 210 kilonewtons. Okay, so I guess we should write um, a symbol here. Let's say a P sub U. Okay, so that stands for the or no, this is shear. Then this should be V. Sorry. So V sub U. Okay, so V sub U, meaning ultimate shear or factored shear. You can write it that way. Um, Factored shear load. So we're still on the load sides. Okay, so the load combination number two, we have a 1.2 dead plus, if we simplify it, we'll have a 1.6 live. Okay, so 1.6 live. Okay, so I still forget to write this V sub U. So 1.2 dead, that's gonna be 1.2 times 150 plus 1.6 times 60. Okay, so what's this value? We have 1.2 times 150 plus 1.6 times 60. Okay, so we have a 276 kilonewton. Okay, um, the next one would be the third combination. As for the third combination, we have this loading conditions 1.2 dead plus. Okay, so the second term we have, okay, we'll just write down 1.6 LR or R, and then the third term plus F1L or R. Okay, so since we don't have this second term, but we have, alright, so for this, sorry, this is F1L or, sorry, this is 0.8 wind. Okay, so that's 0.8 wind. Okay, so we'll check first, since we both have live loads and wind loads, then we'll check first the live loads and then we'll do another computation using the wind loads because it says here or. So 1.2 dead plus F1, F sub 1 live load. So that's gonna be 1.2 times 150 plus, let's assume for now that 1.0, so 60. Okay, so we have 1.2 times 150, okay, plus 60. So we have a 240 kilonewtons. Okay, and then we'll do another, let's say this is 3A, we'll do another load combination 3B. So 1.2 dead plus using the wind load 0.8 wind. Okay, so 1.2 dead, sorry, what's the dead? That's 150 times 150. Okay, so plus, let's say plus minus 0.8 times 50. Okay, so 1.2 times 150. So 180 plus 0.8 times 50. We have a 220 kilonewton, or if it's negative, we have 1.2 times minus 0.8 times 50. We have 140 kilonewton. Okay, so that's the third combination. The next we'll go on to the fourth combinations. So we have 1.2 dead plus 1.6 wind, okay, plus F sub 1 L, and then the fourth term on roof live loads and rain loads, we don't have those loadings. So we'll just simply put it this way. Okay, so 1.2 dead times 150 plus 1.6 times let's say, so this is going to be plus minus 50 plus live loads. Okay, so again we'll assume 1.0 for the F1. Okay, so computing now, we'll get 1.2 times 150, so that's gonna be okay, plus minus 1.6 times 50, 80. Okay, plus 60. Okay, so we can have 180 plus 80 plus 60, so that's 320 kilonewton. Or we can have if we're consider the negative value, we can have 180 minus 80 plus 60. Well, that's, oh sorry, that's gonna be 160 kilonewton. Okay, so far this load combinations produces the largest loads. Now we still have to check. So for the fifth load combinations, we have 1.2 dead plus 1.0 earthquake. We don't have that, so we'll just skip that one out, plus F1 times L. So I think this is just the same as this one. We have a 1.2 dead plus F1 sub L. Okay, so let's just write 240. Okay, so 240 kilonewtons. Okay, so for the load combination number 6, for the load combination number 6, we have 0.9 dead plus, okay, plus minus 1.6 wind, okay, plus 1.6 the soil lateral loads. Since we don't have this, then let's just say this 0. Okay, 0.9 times 150, okay, plus 1.6 times, what's this, wind. Okay, so plus minus 50. Okay, so 0.9 times 50, okay, that's 45 plus minus 1.6 times 50, so that's gonna be 80. Oh sorry, I think this is 0.9 times 150, so this is 135. Okay, so 135 plus 80, that's gonna be 215, or we have a value of 135 minus 80, or 55 kilonewton. Okay, and then the last combination is the 0.9 dead plus 1.0 E plus 1.6 H. So since we don't have the E, the earthquake loads, then this is 0. The 0.9 D, that's just 135. So it's just the same as this value. So 135 kilonewtons. Okay, so if we tabulate, actually, this is this can be presented in a more organized way in terms of a tabulated presentation. So you can write it in this let's say this kind of, or in this in this way. Okay, so we have a loading combination, or let's say load combination, and then what's the factored loads. So if we have our first load combination, let's say it's the load combination number 1, we have a 1.4 dead, and we have a value of 210 kilonewtons. For load combination number 2, we have 1.2 dead plus 1.6 live. Our value is 276 kilonewton. Then for loading combination 3A, we have a 1.2 dead plus F1 sub L, and our value is 240 kilonewton. And for our 3B, we have a 1.2 dead plus 0.8 wind. Our value would be, actually we have two values, so 220 kilonewton, and 140 or 140. Okay, what else? We have loading combination number 4, 1.2 dead plus 1.6 wind plus F1 sub F1L. We have a value of 320 kilonewton and 160 kilonewton. Okay, well, what else? Loading combination number 5 plus F1 sub L, that's 240, and then our number 6 combination, that's 0.9 dead plus 1.6 wind plus minus, we have value of 215. Then we have also 55 kilonewtons. Okay, then number 7, we have 135 kilonewton. Okay, so which loading combination gives the highest value of these factored loads? So you can see we have this these loading combinations right here. So we have a 320 kilonewton. So the goal here is when we compute this load, this factored loads, then these are the ones that we're gonna use for the analysis or for sizing up the member. Okay, so for now we've only considered like a direct calculations, like I've given you the dead load of this value, a live load of this value. Um, let's say for shear, for it could be in bending moments, or it can also be in actual loadings for columns. But what if if it's given in a um, let's say in a drawing. So let's say you have these structures, let's say the floor framing plans, then what's gonna be the dead load and live load? So we will tackle that one on our next section topic, which should be on the tributary areas. Okay, so see you in the next video.